James from Quantum Motion. What we've heard a lot of at the conference, and Unmesh did a good job of teeing me up here, we need a lot of qubits. To do useful things, you know, the Microsoft paper that's come out this year, we need a lot of qubits. And that's what we're about. We've got a really, really good way to realize large numbers of anything, and that really, really good method is the CMOS process. So we can make billions and billions of transistors using this process in CPUs. You know, this is a M1 chip. I decided not to break copyright by telling you that it's an Apple chip, but it is. And why not use that as a model to make qubits? And that's what we're doing. So this is the modern transistor as of about 10 years. And, you know, what we're doing at Quantum Motion is not just making CMOS compatible things. We are using the template that we've been given, a transistor. We're making as few changes as we conceivably can, having single electrons under those transistors, and therefore providing a reasonable way to try to address the scaling problem to achieve billions of qubits in the long run. So that's what the company is all about. I guess taking a step back to, you know, setting the scene, it's hard to solve real problems with a quantum computer at the moment. We've heard about, you know, needing a large number of qubits, and this is one of the resource estimations that we've carried out. And indeed, we heard John Preskill talking a little bit about this morning. So, small toy model, easiest possible, lowest hanging fruit, 5x5 Hermie-Hubbard model. Takes about 50 qubits to simulate that. Let's apply some reasonable estimations of the gate fidelity, speed of execution. It'll take you about a year and a half to come up with a solution. And it's unlikely anyone's going to do that. So we should be looking at parallelizing this. You know, not just asking the same question again and again, but saying, let's put thousands, tens of thousands of cores on an individual chip. And this is something that we can do in silicon. And so that's the sort of first use case as to why silicon is a nice system for us to use. And this is only kind of phase one of what we're realizing at Quantum Motion. So this goes right the way up to a full fault-tolerant universal compute fabric. So this is putting thousands, hundreds of thousands of transistor-like objects, running them as a qubit, and putting all of the additional analog and digital IP on there. And this is what we've shown, you know, most recently. So this is, I know this isn't a technical conference. We'll talk more about this at APS in March, but we've recently shown 1,024 single electron quantum dot devices addressed, characterized. There's about 3 million transistors on this, in addition to the 5,000 plus qubit structures. And these are all addressed via a serial link, so only nine electronic contacts going up to room temperature. And that's why we think it's a neat approach. And if we can learn the lessons that we've learnt from the silicon revolution, then this is our route to, you know, fast track to a useful quantum computer. And that's what we're doing at Quantum Motion.